Hello everyone. So we are having our lecture 20 microelectronics EE341. So last time we discussed about regarding the sends and the return and different configuration, the shunt, series, shunt or shunt series, ultimately the voltage, current, voltage and voltage current amplifier or feedback. And we saw how the input output impedance changes in each configuration and also the gain. And we left some of those for your own. We just did basically for the voltage and current voltage, and we left the voltage current and the current for your own analysis. Make sure to do that thing, for that practice is very much helpful. Also, we got to know that you might have some issues on the how to check the polarity of the feedback, whether it's a positive or negative. Just I can again quickly tell the rule of thumb, but you can also refer to the last year lecture, which are also uploaded on the same YouTube link. It's a lecture 2 basically, and lecture 1, both are talking about the polarity. But the thing is that we just need to have a network which is available to you. For example, here something plus, and here y, which is going as k and something. So for the feedback, what you need to basically do in order to determine the feedback, you need to separate this path that, okay, you increase this point x, either it's a voltage or a current, and see its effect on the y. Okay, so you saw its effect all the way to the y. And when you reached here, you will see that this is impacting this node too. And you will transverse back here. And you will see the response, whether you and your intention was you want to increase this node and the feedback is doing what. If it's in agreement with that thing, meaning it's increasing ultimately here also, good job, it's a positive feedback. If it's opposing it, this means a negative feedback. So you can just analyze accordingly. So you might be a bit confused on the voltage and current, but what you can do a little bit examples. And again, if you have any concerns, specifically do come in office hours, we can discuss and we can do more examples. But the main thing is that you need to have those previous fundamental understanding that if it's a voltage, if it's a current, common source, common gate, source follower, how the input to output things are going to be. So just like, again, try to do those things and hopefully you will be able to identify. But the main thing that I would like to reiterate again, that if you have, for example, input here and output here, and V out. If I say that V increases, what will happen with the V out? So we can see multiple ways. That was the main point. This is a common source amplifier, right? So it's a common source amplifier. If I do ground here, so if I V in increase, it's a common source. Common source is inverting. One thing, in any case, I can say the V out will go down. Okay, that's one way of seeing it. Another way of seeing is that V in is going up, meaning VGS is going up. This means the current which is flowing through here, ID, will go up. And as the ID will go up, the V out is what? Equal to VDD minus IDRD. So you can see in this way too. Again, because of this thing, ID is going up, V out will go down. So the same thing, V out will go down. And now it's connected to the feedback of somewhere, and then you can see whether it's doing a positive or negative, you can conclude accordingly. Same thing applies to where there was some confusion in the common gate one, where you have something, we are applying, for example, a current here, I in, okay, and you are asked to find, for example, RD and VDD. And this is a V out. Now, if I in is going up, for example, if my I in is going up, what's going to happen with my V out? Again, this I in is going here and it's going to be converted into some voltage. So if I in go up, this voltage or Vx here will go up. If this voltage will go up, what will happen with the V out? Since it's a common gate amplifier, the voltage will also go up because it's a non-inverting in nature. So that's what we need to see. So V out will go up. Or if you want to see in terms of a current, I in will go up. So the ID which is flowing from here will go down. And if ID will go down, this means the voltage V out, which is equal to VDD minus ID, RD will go up again. So that's the way you want to see. So you can either see in the common source, common gate or source follower configuration, or you can see in terms of how the things are changing as you increase or the current or the voltage. You can play around with that thing. So make sure this small identification how the things are happening. Okay, and then something is coming as a feedback as a current here, and you can identify. And also if source is input is current feedback will come out. If source is volt, input is voltage, or source is voltage, then voltage feedback will come here. So that's also we need to identify. So make sure to break the circuit, and then you can identify easily things. Let's move on towards today's topic. So what we are going to do today, we are going to conclude basically chapter 12 today, and the section we are going to mainly talk is 12.18 from your Fundamental of Microelectronics book, and the topic is again the feedback. But one of the most important thing in the feedback system, and that is stability. And I assume that most of you are already familiar with the stability since you have seen this thing in your feedback course, feedback and control course. But we just want to have some review of the things and apply into some examples related to the circuit. But the concepts are exactly same which you have seen in the your control course. So today's lecture, I would rather say it's a review lecture for most of you. But the things are again fundamental. So we talk about open loop. We have an input voltage goes to a block or amplifier with the gain V. When there is no control, we say it's an open loop system. Okay. Open loop system directly applied to an output, directly depending on input. If input is any value, A is very much bigger, output can be accordingly. Okay. So we are concerned with the things that how much the A should be, how much the V in should be. So those were the challenges which we went into it, and then we don't have precise control. So then we said, okay, we can have a system where we can have something like this. We can have an input which is going here. We can have the same amplifier or gain stage going to our output. And then there's a feedback which we call a negative feedback at this moment. Right? And we have here, so this thing. So we have a system where this sign is ultimately deciding what we are doing. If this is negative, this is a negative feedback. It's more easy in this block diagram as compared to the amplifier where you have to see. But if sign is positive, this means it's a positive feedback. But in circuits, we need to identify, we have seen how to find the polarity. But most of the system which we want to work with, they are negative feedback system. So most of them are negative. We already talk about some examples of positive feedback system, which is an oscillator or the memory, the latches basically where we want to store the data. So those are basically the positive feedback system, but mainly we in this course or in this content, we want to talk about in terms of negative feedback, where we want to give a negative feedback system and we want to see that the system is stable. And that is very much important. What is meant by stability? Something similar. Here we are giving this input, fine. We have some gain 100 times. This will be amplified by 100 times. Fine, well and good. We don't have any issue. We can set the gain accordingly. It's not precise, but still system based in our control. But here, what's happening, continuously feedback is giving. We have input here and we have some gain here 100 times. and then this is going output, and ultimately what's happening, we have some sort of a feedback. If it's a negative feedback, ideally the system should remain between know that here the output should be V out by V in should be equal to 1 A divided by 1 plus KA. Okay, so and for very much bigger value of A, for A is equal to very much bigger, then what we can have the V out by V in is equal to 1 over K. That was our intention mainly, that if A is very much bigger, or KA is very much bigger, for example, to be precise, then gain or the closed loop gain will be equal to 1 over K. So we can have a fixed gain. But in some circumstances, what we do ultimately, instead of having this magnitude as a negative, we might convert into a positive feedback because of our poor design, because of not doing some consideration. How? You know that there is something magnitude, and then another thing comes as a phase. Till now in this course, we didn't touch the topic of the phase, and phase is very much important. Phase can make the system unstable even your magnitude is positive. For example, if a positive magnitude is considered a negative feedback, but if the phase is more than 180 degree, the net conclusion is going to be a negative, and then ultimately you are in totality giving a positive feedback. So that can be one of the biggest issue which we go into. I will describe in terms of quantitative in a moment, but the challenge, for example, is that you have ultimately system which I just drawed here, and you end up in this thing. You have something positive, and then your response positive, and then ultimately it starts becoming like this. With the passage of time, it starts first oscillating and starts becoming out of control. And when the thing becomes out of control, they become unstable. And that's something which we don't want. We don't want our system to become unstable. In any case, we don't want the system to be unstable. Okay. Even in oscillator, the system is still stable. It's oscillating, but it's oscillating at a specific frequency. It's not changing, it's not enhancing. But when something starts enhancing like this, with the passage of time, this means the system is unstable, and we don't want this thing. But we are going to talk here the negative feedback system and how we can avoid system to oscillate, and how we can avoid the system to become totally out of stable or totally enhanced or increased version and go to infinite. So for us, both the thing oscillation also not stable for us. So keep this thing in mind. Oscillation for our design is also not stable. And the other thing is that increase with the passage of time, because oscillation is not increasing with passage of time. It's still remaining stable, but that's what we don't want. Increase with passage of time. So both are the things we don't want in our negative feedback system. And that's what we say. We don't want these two conditions to happen to our systems. So let's go back and see a common example of a common feedback amplifier. Basically, it's not like a common gate. I'm just talking about a feedback amplifier, rather standard feedback amplifiers. Feedback amplifier. So in feedback amplifier, what we have seen, we have a amplifier. Okay, we have a polarity. We have something here output, and this one is grounded, and we have something input. We normally call it. So it's a voltage, and we have a resistive feedback. The same which we have seen in the last lectures. It's a voltage to voltage feedback, meaning shunt series connection. Okay, sensing is shunt and feedback return path is series. Okay. So we all know if we want to talk about V out over V in this configuration, we will ignore the A, which is A is very much infinity, let's say very much bigger value or KA. So we will talk about gain as minus R2 over R1 since it's connected to the negative one. So it's an inverting configuration. Okay? Or we can convert into a simple amplifier. VDD. Here we have an RD. We have input here. It's the same thing. We just draw it and then we can mimic in a different way. And we have something R2. So you can analyze both of them are the same thing. And here you have V out. Right? So we can just directly mimic this circuit that this is going to be like this. And we are assuming that GMRD is very much bigger than 1. Okay. So we are assuming this thing, and also R1 plus R2 is also very much bigger value than RD. So these two considerations we are doing. So the meaning of these things that overall KA is very much bigger than 1. So once the KA is very much bigger than 1, we are going to have V out by V equal to minus R2 by R1, which is a K in this configuration. 1 over K in this configuration is equal to 1 over K. But now we know that we need to identify the stability in our circuits through some way. And what is that some way? Is basically something similar, which we have previously talked about. That's why I was saying it's a review for you. Even we have talked about the Bode plot, but we are going to talk again the Bode plot and bringing this time the stability effect, meaning we are going to bring also the phase in the equation or in the overall scenario, how the phase behaves or how we can draw a phase from a circuit. Okay, so we are going to do a little bit again review of the magnitude response and then also about the phase response, so that you can just a little bit get relaxed that okay, we are not covering something new, rather we are just reviewing our old friend, which is a Bode plot. And again, you have seen this, I assume, a lot of times, or that's a fundamental in your control course. So again, going back to the same dynamics, where we have a gain, frequency dependent gain, which has some poles and some zero information. So for example, we have 1, 0, A over J omega Z by Z divided by 1 plus J omega by omega P1. So I'm just drawing 2 poles and 1, 0, just to clarify. But you can have any system. Okay? So it's not bounded by this one, but you can have any system. Right? So we have basically 1, 0. Okay, this is a 0. And we have 1 pole here and another pole. Okay, the first pole and second pole. And we all know that in a system, we have equal number of zeros and equal number of poles. This means if we have 2 pole and 1 pole here, the other pole is going to be at infinity. So we have 1, 0 here and other 0 will be at infinity, but we are not concerned with that one. But all the time in any system, the number of poles is equal to number of zeros. If no zero is drawn, this means both the zeros are at infinity. So, but we are concerned about the magnitude response first. Again, we will do the phase too, but let's start with the more easy thing, which is a magnitude plot for us. So if we talk about magnitude, we will take 20 log just to convert into dB and A times omega with the mod values. This means we are taking magnitude response. If I want to draw this thing, this means I am taking individually 20 log, open this thing 1 plus J omega, omega, I'm just writing again, omega Z. Now when we are taking the log, but we can do division will become subtraction. So we can directly write minus 20 log 1 plus j omega by omega p1. What will happen here? Again, minus 20 log 1 plus j omega by omega p2. And what about the phase? For the phase, we can write simply phase is equivalent to something like this. We normally write using the black color again. So for phase, for angle, we can write angle of 1 plus j omega by omega z minus, again for our denominator, we will use the minus sign, subtract with 1 plus j omega over omega p1 minus angle of 1 plus j omega over omega p2. Okay, so that's what we can easily write. So that's the overall the Bode plot which we normally use, and then we need to just do the approximate plotting. So the first thing is that we need to write the magnitude and the phase plot, and that's the more than half job is done. So first thing before moving forward, we need to see for the zero. So I'm just talking about this zero part. I'm dealing individually, so I will write the color code. This is I'm going to green, this is I'm going to yellow, and this is blue. So you can just see. First, I'm going to talk about the magnitude, and the yellow color is talking about the zero. So magnitude 0. Okay. So magnitude of 0, we can bifurcate according to Bode plot into configurations. Those two configurations are those when omega is very much less than omega z, and another one when omega is very much bigger than omega z. Okay, so I will write it for omega very much bigger than omega z. And we mentioned last time, or when we did the review, that omega very much less than omega z. This means that omega is equal to, for us, we can take omega is equal to omega z by 10. So factor of 10 is enough. 1 decay is enough. Omega bigger than omega z. Again, these are just approximations, so we can have some plotting. It will give us idea. It will not give us the actual values to be exact. It will be near to the actual one. Okay, but that's enough for hand calculation. We don't using calculator. We're not using some software tools. From our hand, we can have an idea. So if for first case, if omega is less than omega z, what's going to happen? What will be happening with this thing? So let's plug it and see. When omega is less than omega z, so 20 log, what I can write? Omega is very much less than omega z. This factor will become equivalent to 0, right? So we are having 20 log of 1. Agree? We are talking only about the magnitude. So we're not concerned about the j at this moment. So at this moment, we are going to have 20 log of 1. 20 log of 1 meaning 0. So this will become 0 dB. So for any value which is any frequency which is at least 10 times or less than omega z, this means the magnitude is going to be 0. That's well and good. But I am meaning something. Again, I'm drawing in yellow magnitude response of omega z. So for example, if this is omega and this is omega z here for me, so I'm saying anything, if this is omega, which is 10 times less than omega z, so this is point is omega z by 10. So till this point, I am going to have a 0 dB. Okay, all of you are clear till this point? So till this point, my magnitude, only magnitude, meaning mod of a of omega for 0, and talking only at this one 0, I didn't bring any pole, and I didn't bring anything else till this point, omega z by 10, my magnitude will be 0 dB. What will happen as I increase? So if I am going to have a bigger value, meaning omega z, the omega is 10 times of omega z. Okay, if I 10 times of omega z, so what I am meaning ultimately, I am writing something 20 log of Az of omega, which is equal to 20 log of, if I just ignore, because the one is going to be ignored in terms of magnitude, we will be left with something like this, equivalent to we are having a very much bigger value, which will be depending on this mega z factor. Okay, and that will be ultimately resulting into this term. If I have a bigger value which is depending on this factor, then ultimately I can easily represent that I can write this 20 log omega by omega z. And what does this mean? This means I can ignore this omega z factor, and that will be totally depending upon whatever the value coming. So that's why it's going to have a ramp increase all the time onwards from this point based on the ratio of omega and omega z. So it's 20 time multiplied by 20 dB per decade. So it will have a ramp which is going to be enhanced based on this value. ठीक है यहाँ तक? And what will happen till this point? जो यहाँ point है, to be exact, we can find out what will happen at omega equal to omega z, since we are having this factor. So at omega equal to omega z, we will have 20 log 1 plus 1, which is equal to 20 log, yes, square root of 2 ho jayega if we talk about magnitude response, and we will be left with 20 log 1.414, which is equal to a 3 dB point. But we are not concerned with this thing. We can, in approximation, we can write, okay, ultimately at omega equal to omega 0, we can draw that this is equal to 0 dB. And as we start increasing after omega z, we will be having a 20 dB per decade. So this will continue onwards. We are not concerned. As we increase from omega z, omega will start increasing from omega z, it will be starts increasing from 20 dB per decade. So that's one thing. The vice versa will apply ultimately for our z poles. What will happen for the poles? Everything else remains. Now we have 20 log 1 plus omega by omega p1. This means for omega very much less than omega z, meaning 10 times factor, the gain value will be, magnitude will be equal to 0 dB. And for very much bigger value, it's not z, p rather, p1, the omega v will be equal to 20 dB, but with a minus sign, omega by omega p1. So whatever the values come, it will accordingly calculate from that number. So we just need to find, rather I shouldn't write dB here, write 20 log of this. So meaning I will, if I want to do a plot, I will just do some plotting and you just get again ramp up on the thing. So omega here, so omega p is going to this direction. Omega p1, if for example is at this point, so from till this point is going to be 0 dB, and onward is going to have a minus 20 dB per decade. Okay, so that's one of the things. Now, if we have some expression which we just have in a previous window, overall expression, meaning a of omega equal to 1 plus j omega by omega z divided by 1 plus j omega by omega p1 times 1 plus j omega omega p2 If we have this expression and we are told that omega z is equal to 100 times of omega p1 and omega p2 is equal to 100 of omega c, meaning that the first pole which is going to be coming is omega p1 followed by omega z followed by omega p2, and all of them are separated by 100 just for a simplification. So let me draw the magnitude plot here. So for the magnitude plot, if I want to do this thing, let me use a different color. So initially, let me start with a 0 dB and I point out these points. So this is, for example, point of omega p1, omega z, and omega p2. And it's not omega 2, this is omega z. So till here, I am going to have a minus 20 dB per decade starting. But 10 times of this one, it will start getting stabilized. Or sorry, here. And once I reach at this point, it will start getting further on stabilized. Okay, because minus 20 plus 20 dB, they were cancel out themselves, and then also here starts. So this is minus 20 dB per decade. This is 0 dB per decade, and this is minus 20 dB per decade.